Yeah. Good job. Okay. Not take too much time on that. Well, can somebody like maybe we can dim the light there or turn it off? Lights. The lights. I think it might be just that switch. Don't hit the panic. Be panic. You thanks to anybody see it? I was told there's a panic button. I see the panic button. Really? Well, it's like how to use the panic button. That's the sign. There's a sign, but maybe it's back here. Maybe it's back here. I don't see it there. Okay, well, all right. I'll have to let them know that they have a sign, but no panic. Okay. All right. Hopefully, you never have to use it. All right. Let me get started for today. Here are sort of a summary of our topics for today. We'll cover light interaction with matter. We just started on that last time. Scattering, interference, absorption, all those good things, and refractive index, and the wave picture. I don't think we'll have time for today, but probably this week we'll get to that, as well as maybe some other stuff on Fermat's principle. Okay, so quickly to review, in the last class, I started telling you that all of the processes that we think about with light, propagating through air or glass or water or any transparent medium or even non-transparent medium can be viewed as, things like reflection, refraction, etc., are manifestations of scattering of light on a microscopic level. And of course, we know at a microscopic level, matter is made of atoms and molecules. And so we discussed in the last class that we can model this scattering of light. And remember, I showed you that the intensity, which is the irradiance or intensity, which is what most of the time is what our eyes are sensitive to, certainly, and also what many detectors will detect. So if you use a CCD camera, when you take a picture with your phone, when you or if you're old school and you take pictures with photographic film, whatever it is, most of the detectors are sensitive only to the square of the electric field. This guy over here. And so the intensity, which is proportional to the square of that electric field, goes as 1 over lambda to the 4th in Rayleigh scattering, when it's like small atoms or molecules, which are smaller than a wavelength. And as you can see, this is strongly dependent on the wavelength. And we've discussed that blue light, which has got the shortest wavelength, will be preferentially scattered more out of the molecules in the air. And so what you'll end up getting is red or yellow or orangish light, depending on the amount of scattering, etc., that happens as the beam travels through the medium. Okay, and this is the reason why the sky is blue. And we also talked very little, briefly, I mentioned to you that this is also true, say, in liquids, because in liquids, even though you can't think of them as like a rare medium, like, they're or you can't think of them as just like one particle or small numbers of particles. But what happens is that there are fluctuations in the density of the liquid, which on a small volume, these rapidly changing density fluctuations will have a similar dependence. They'll look like, this is what Einstein and Smoluchowski showed, that due to thermal fluctuations of the number of particles in a small volume, then again, those fluctuations, if they are significant, will again scatter light similar to a single molecule or a single atom. Okay. All right, so now we started to talk about this, but we didn't have time. So first of all, let me remind you that the fact that there is light entering our eye, it comes from many different scatterers located in space, right? Because it's not just one scatterer or one atom or one molecule, there's lots of them, okay? And so we had to think about what happens when lots of these waves are coming and, at some point P. Well, so imagine that the sun is over here, just mentally, there's a sun, and it's sending out beams of light, rays of light, or in this case, plane waves. And these plane waves hit these atoms or molecules up in the upper atmosphere. And these atoms or molecules are scattering light. You could think of this as the waves, or you could think of them as just rays coming from that atom. And if you remember back when we discussed the wave interference or wave superposition, I mentioned to you that when a crest and a crest coincide, like a maximum and a maximum of two waves coincide, you get constructive interference. You get, twice the amplitude of the wave. And if a maximum and a minimum coincide, that is one wave is at a maximum, the other wave is its negative maximum or a minimum, right? That's a negative maximum. So then it's a plus minus combination, right? Plus A and minus A combining. And so those two will add destructively and you'll get zero amplitude. You'll get negative or you get destructive interference, okay? So what happens then is that if we looked at all of these atoms, some of them, because they're randomly distributed in space and they're far apart, they have like various types of phases, okay? And some of them, because these atoms are randomly distributed in the upper atmosphere, some of them will act constructively, some of them will act destructively. So eventually, basically, the interference will disappear. Okay. So if interference disappears, what's left? Well, we can just think of them as independent scatterers. Okay. We don't have to worry about the fact that the waves are adding up in phase or out of phase because that interference term disappears. That E1 plus E2. You can just think of like each atom not knowing anything about the other atoms. So what will you do then? Well, if I were to just add up each of the atoms individually, each of them will give you some intensity at your location, and the sum of the intensities is what you'll observe. Or if you want a slightly more mathematical argument for that, what I can say is that normally, as I just said, suppose I have two waves, then I need to add up the two electric fields. We did it as psi1 plus psi2, but I'm just writing it as electric fields, E1 plus E2. And then we said that the intensity is just proportional to this term, E squared, right? So that means that it's just equal to E1 plus E2 squared. And of course, when I square both of these, I'm going to get a term, E1 squared plus E2 squared plus this 2 E1, E2, and okay, so because these are sines and cosines, it turns out that there will be a term which goes as cosine of the phase difference between them. Okay, that's what we saw, or equivalently, you can think of this as when the phase is the same, E1 plus E2 add up to give you, suppose it's constructive interference, and let's say E1 and E2 are identical, then I will be proportional to 2 times E naught, let's say E1 equal to E2. Okay? Let's say E1 is approximately E2, is approximately some value E naught. Then this term will be 2 times E naught, the whole square, which is 4 E naught squared. And of course, the intensity of any one beam is just I naught is this E naught squared, right? So we're getting 4 times the intensity from any one scatter if there's constructive interference. And of course, in destructive interference, the two of them will subtract, E1 minus E2, you'll get 0. Okay. But when you have random phases, this delta phi term, which is the phase difference between the two waves, I'm not proving this result. Later on, we'll see it in interference, that this is exactly what happens, that there's this interference term. And this interference term, when it averages over all the different phases, this delta phi can vary anywhere between 0 to 2 pi, and it'll end up just averaging out completely. Okay? So that interference term disappears when you have a collection of random scatters. So then you're just left with E1 squared and E2 squared, which is just, of course, each individual intensity. So you're adding up the two intensities. So when all the interference terms disappear, you just get the sum of the intensities from each of the individual scatterers. Okay. Is that clear, that argument? Any questions? Stop me if you want to go. Okay. And in that case, oh, sorry. So, yeah. So that's all I wanted to say here. So that's why we can just think of the Rayleigh scattering from the upper atmosphere as just a sum of the intensities from each of the individual scatterers. And we know that each of the individual scatterers, the intensity is proportional to 1 over lambda to the 4th, right? So it's going to be bluish light that is scattered to us, and it's just a sum of all those bluish light that we are seeing from those atoms in the upper atmosphere. You may also ask, well, what about the, we were looking at lateral scattering, right? I mean, we were down here, the atoms were up here. What about the direct scattering? What if I was looking directly through that medium? Why do I even see any transmitted beam at all? Because by the same argument, you might say, what about the positive phase differences, negative phase differences, and all that? Well, it turns out that in the forward direction, and we'll come back to this when we discuss interference in more detail, but they add constructively with each other in the forward direction. Okay, so basically what I mean is that if you look at a wavefront coming from, say, point A, you get this first wave that is transmitted from this point A, from the incoming beam. And this first wave, okay, there's one more little, wrinkle that it's not in phase with the incoming wave. It's 180 degree out of phase, but that doesn't matter to our argument, because all I'm saying is that instead of the scattered beam being in phase with the incoming wave, it's 180 degree out of phase with the incoming. Okay, so that scattered beam, and then the next one from here, this is another point B, which is over here, and this point also is emitting this scattered wavefront that is 180 degree out of phase. Together, these two will propagate in phase with each other out going forward. And that's mainly because you can think of it as the transmitted beam, the primary wavefront breaks the symmetry and gives rise to this transmitted beam. Okay, if you didn't follow all of that, it's fine. It's not a super important thing to know, but in case you're wondering why in the forward direction we see a transmitted beam, this is the reason. Okay. So let's now talk about dense medium, meaning medium in which the atoms and the molecules are clustered together much more closely. Okay. So in much denser media, for example, in the lower atmosphere, it turns out there are millions of molecules in like one wavelength cube size volume. Okay, so there's a lot of molecules in the upper atmosphere. As I just said, there's a large lateral scattering. We can sum the intensities of all the beams in the lateral direction. So in the lower atmosphere, however, it turns out the atmosphere, as it gets more and more dense, the lateral scattering is more strongly suppressed. I'll show you that in just a second in a slide. So here, what is happening? So this is the reason, for example, when we look at the sun directly at sunset or sunrise, that the sunlight is propagating through a lot of the upper atmosphere and coming straight into our eyes. And so of all the lateral scattering from the which is bluish, right, is going to be scattered outward away from our primary direction, which is the primary direction is just straight staring into the sun. Well, don't stare directly into the sun, but you get what I'm saying. So then, as you can see, what's left behind is the reddish and orangish light, which is what we are seeing at sunrise or sunset. By contrast, you may ask, what happens if I look at, say, the light from some mountains or some, I'm sure you're all familiar, if you look at some mountain range in the distance, it often looks bluish rather than reddish or orangish. Yes?
I think is this due to the Raman scatter?
No, not this effect.
Okay.
This is not Raman scatter. Okay. So in this case, what is happening is that the light which comes from the mountains is going primarily through the lower atmosphere. Okay, so it retains the bluish and orangish light, the bluish and green light, because that's lower atmosphere is very dense and the lateral scattering is suppressed. Okay, so there's no scattering of the blue light out of the beam that is coming towards us. So we still see the blue and green components of that light that's coming through the lower atmosphere. Okay. Okay, and this is what I was just trying to say. and the reason, okay, so now the reason is why is it that in the dense medium, so I've broken it up as like very less dense medium like upper atmosphere and very dense media like the lower atmosphere, or as we'll see in a minute, like other things like like glass or water or any of these other things, they're all going to have this phenomenon, which is that the lateral scattering is going to be strongly suppressed. Okay, and why is that? Well, that's because for example, in the lower atmosphere at STP, this has about 3 million atoms or molecules in a wavelength-sized cube. So think of a cube whose sides are 1 wavelength by 1 wavelength by 1 wavelength. Okay, so for green light, that's 500 nanometers by 500 nanometers by 500 nanometers. Okay, so in that small volume, it turns out there are 3 million molecules of air. Okay, oxygen, nitrogen, whatever. So each of these, so for a minute, just assume I arrange them in a grid, just for simplicity, to make the argument easier. Of course, they're not doing that. They're moving around a lot, but Einstein and Smolachowski have already told us that that's okay. We can still approximate this as individual molecules that are separated by this distance. Okay, so what's happening is that imagine I take two such atoms, A and B, which are separated by half a wavelength. Okay, lambda over 2. They're separated in this direction by lambda over 2. So that means that any waves that propagate outward in this direction are going to be out of phase by lambda over 2 as they propagate out in this way. And we just, as I remember, I told you, when two waves are separated by lambda over 2, what kind of interference is going to take place? Constructive or destructive? Destructive, exactly. So these two waves are going to cancel out in the lateral direction, but in the forward direction, they're okay because they're going to have, the same phase in the forward direction. They are only separated by lambda over 2 in the transverse or lateral direction, so therefore they cancel out in this way. Of course, you can ask, what about these other waves that are separated by lambda over 2 from each other in this direction? Well, that's what that old argument was about, which is that in the forward direction, they're all going to add up constructively. And so I won't go back to that for now, but basically that is the reason why we still see the forward beam. And we'll come back to this when we discuss interference and diffraction in more detail. So the forward direction still experiences, the propagating beam or constructive interference. Yeah, and this is just showing you all of that in much more very great detail. So we just drew a few wavefronts here. Here they're showing every single atom in that grid, and they're showing all the different wavefronts coming out from that, and they're adding it up. And you can see here, like, these waves over here. And in this case, the beam is traveling like this. Sorry. So just take this picture and flip it down. Okay. So the beam is going this way. Okay. Rather than from left to right, it's going from top to bottom. And we can see that these wavefronts are going to constructively interfere in this direction. But out here, you can see it's just a jumble of like various wavefronts with like all different phases and so on. And so they're just going to basically disappear after a couple of wavelengths. So you're not going to get a strong laterally scattered beam in this direction. It's just randomly, it's a mess of all the different wavefronts, so they cancel out. Okay. All right, any questions about this? So I guess the main thing to take away is in rare media, you're going to see more lateral scattering. In dense media, you're going to see less lateral scattering or almost zero lateral scattering. And by dense, I mean just something like the Earth's atmosphere down here. We don't think of the Earth's atmosphere as being dense because, you look out, you don't see anything there, right? It's not like you can tell that there are lots of atoms and molecules. But as far as light is concerned, there's just millions of molecules in a small wavelength size cube. And so there's always some atoms that it can find to interfere with and suppress the lateral scattering. And that's what matters for the lateral scattering or the lateral beam. So we can neglect that in dense media like the Earth's atmosphere or anything denser than. Okay. Oh, sorry, this played out of sequence. Okay, I'll just talk a little bit now about index of refraction. So in a dense, homogeneous and transparent medium, something like glass or water or quartz, any of the things that we think about as being solid and, or liquid, but, somewhat having a lot of atoms and molecules in them, okay, the atoms are now going to be spaced even closer than in a gas, right? So they're much smaller than a wavelength, okay? Sorry, this was supposed to play in a minute, but so just ignore the figure for a minute. And so now again, it's the same thing. The scattered light from each atom combines with the incident light in the forward direction to create a transmitted beam, okay? But there is one other effect that I'm going to tell you about now, that due to the phase shift between the scattered light and the incident light, the transmitted beam will travel with a slower velocity in this medium. So I already told you that there's going to be only the forward direction, the forward beam. We can neglect the scattered components, the components that are scattered out laterally. So there is a transmitted beam, the forward direction. And the main difference between, if there was nothing, if there was vacuum, of course, we know the beam travels with the velocity of light, right? Speed of light, c, which is 3 times 10 to the 8 meter per second. Well, it turns out in a dense medium, which is, dense and homogeneous and transparent, let's neglect absorption for a second. So it's not like it's immediately going to die out. The beam just goes through things like glass or water or, other plastic, there are lots of materials that are very transparent, right? Diamond, etc. So the atoms inside are so closely spaced, again, that we can neglect the lateral beam. But it turns out that due to the effects of scattering, that the beam that is transmitted is going to have a typically slower velocity inside the medium than it is outside the medium. So why is this happening? Okay, so let's talk about that a little bit. So remember in the last class, I told you that a famous model, the way in which we understand the effect of scattering or the reason why there's scattering from an atom or a molecule is we think of the atom as having a little electron cloud. We think about like orbitals of the electrons in an atom or molecule. And these orbitals, when light is incident on them, the electrons move around at the frequency with which the electric field is vibrating, right? And so we can think of the atoms as being essentially when the frequency of the light is, say, smaller than the resonance frequency of the orbitals. Remember, we talked about, there are gaps in the energy level, right? Like hydrogen has certain gaps. Every atom has certain gaps in its energy spectrum because of quantum mechanics. So as long as the energy is below these gaps or in between these gaps, we can just think of the atom as a damped-driven harmonic oscillator, okay? So essentially, the cloud of electrons is vibrating a little. It's vibrating at the same frequency as the optical field, as the electromagnetic field that's incident on it. And this vibrating electron cloud is a charge that's vibrating. And by Maxwell's equations, it means that a vibrating electron cloud serves like an antenna. It re-radiates the electromagnetic waves. So there's now that's what the scattered wave comes from. That's what we discussed. That's why we get a scattered wave. That this cloud of electrons is vibrating, and it gives rise to a scattered wave that comes out from the atom, okay? So if you think about a damped-driven harmonic oscillator, okay, this is recalling some of your 174, 175 stuff. If you have a harmonic oscillator and I drive it, then when it is exactly on resonance, the amplitude of the harmonic oscillator will be a maximum, right? Everybody knows this?
What is the frequency coincides?
With the resonance frequency, correct. So the x-axis is the frequency of light, okay, or omega, okay, about 2 pi times the frequency. And omega naught, which is this line here, is the resonance frequency of the oscillator. So our model is, think of the atom as like a little oscillator which is being driven by the electromagnetic field. In addition, we add in a damping term, because otherwise, as you know, if you didn't have damping, this peak would be infinitely large and it would be infinitely short, because it's exactly at omega equal to omega naught, only that you get a maximum response, and outside of that, you get no response, right? That's what would happen to a perfect harmonic oscillator that is being driven at some various frequencies. But because there's some damping term, this frequency is slight, this resonance is smoothed out. It has a finite width. This width is, of course, proportional to the damping. Everybody familiar with this? Makes sense? Anybody? Yes? Okay. Okay, so and the two cases, what do you think this is due to? This dashed line and the solid line. What is the difference between them? One seems wider and one seems narrow. What do you think is that is due to? Any guesses? Yes?
Damping.
The damping, exactly. So which case is more damping, which one is less damping? Yeah, exactly. So when there's more damping, the resonance spreads out. When there's less damping, the resonance is narrower and also more strongly peaked, right? We can argue that by just the limiting case. If you have completely damped oscillator, highly damped, there's almost no response and it's just completely broad, right? Yeah. And if there's very little damping, then the peak is very narrow and it's very high because now the oscillator responds very immediately to your driving force. In addition, there's a phase. This is something you may or may not recall from your harmonic oscillator stuff, that you read back then, but this is a very important effect. In fact, this is the reason for the refractive index. So I'm going to go over this in a little bit detail. Okay. So if I look at this resonance, it turns out that below the resonance, the harmonic oscillator will be, very far away from resonance. If the force is at, say, some frequency, the response, that is the oscillations of our harmonic oscillator, will be at the same phase as the driving force. Okay. So the driving force and the response will be the same phase, that is zero phase difference over here, or phase lag, as I've written it on the y-axis. As I start approaching resonance, this phase lag goes up to 90 degrees. This may be you may understand this because when you pump a swing, you always have to pump it exactly at like the peak of it's like you go down there and come back, you pump it, right? And you go there and come back, you pump it. Okay, so that's like the 90-degree phase term. Okay, and then as you go further and further away, higher frequency, you end up being 180 degrees out of phase with the incoming field, with the incoming driving force. Okay. It turns out, and remember, I was just telling you that the secondary wave is phase shifted with respect to the primary wave. So there's a 180-degree phase shift because of that. So, sorry, I guess it says 90 degrees. This is, that is weird. So there's a mistake either in that one or in this one. I have to go back and check. Okay, ignore that previous one. Let's assume this one is right. So I told you that the harmonic oscillator this is the phase of the harmonic oscillator. In addition, the scattered wave has an extra phase, which I was just telling you about. Either that one is wrong or this one is wrong here. It says it's 90 degrees. Okay, I'll have to go back and check this. But this, let's say it's 90 degrees for now. It doesn't seriously matter for our discussion because I'm just trying to tell you why there's a phase shift to begin with. So you see that the secondary wave now is in this part of the curve, which is, remember, this is for omega lesser than omega naught, below resonance. The scattered wave is going to have a phase shift of between 90 to 180. Oh, maybe they drew it for exactly 180 degrees for on resonance. So when it is on resonance, it'll be exactly 180 degrees out of phase, which is what I was telling you on that earlier slide. Okay. So, but for omega less than omega naught, the phase shift will be anywhere from 90 to 180. For omega greater than omega naught, the phase shift will be between 180 to 270, which this I wrote as a phase lag, meaning the phase of the oscillator is slightly behind that of the incoming wave. And in this case, it's 90 degree out of phase. So if the incoming wave was a cosine wave, this would be a sine wave, right? And then this would be a cosine wave with like minus sign in front of it. And then, but back here, again, we are back to having a sine wave, except the sine wave is now phase shifted 90 degrees ahead of the original wave. Okay, so if you don't recall that, you just go back and think about all the trigonometric phases and terms in the different quadrants, and you'll understand this. So the point is that in this part, if I call this a lag, then when it goes past 180, it switches to being a lead of the phase. So it becomes like a leading phase versus a lagging phase. That's the only difference. But it turns out when you have a lagging phase, and I'll explain this in a second, then we can represent that as having a refractive index greater than 1, and the velocity, the phase velocity of the wave as being lesser than c, the speed of light in vacuum. Conversely, if the wave has a phase lead, that is, it's leading in phase, now the refractive index can be written as being less than 1, the phase velocity as being greater than c. Does that strike anyone as strange? phase velocity greater than c, right? Seems to violate special theory of relativity that we can have anything propagating faster than c. Yeah. Okay, we'll come back to this another bit. But okay, so now having said that, you may be wondering, okay, I don't see it. So what if the extra phase is there for the secondary bit? Why does that result in a velocity change with respect to the original bit? Right? It certainly puzzled me when I was first told this. Okay. So we will explain that now. Okay. Or maybe it doesn't bother me. If it doesn't bother me, I'll move on. Okay. But okay, it bothered me. So I have to tell you. Okay, so what we have, the basic way in which I'm going to argue that indeed the fact that there is a phase lag or a phase lead of the transmitted or the scattered wave results in a different velocity for the wave is by thinking about what happens if I have a small little slab of material. So I have some incoming wave, E, okay, and let's say it's cosine kx minus omega t. And then I have a little slab of material, which is say delta x, okay? Right. And and we're going to now assume initially that if the slab of material were not present, I could tell you what the phase would be at this point over here, just past this little slab of material. So what would be the phase, or let's say the amplitude of the field over here? And let's say we've run both delta x and delta t forward a little bit to let the wave propagate from the point here to the point there. What would be the wave over here? What would be the expression? So the wavefront over here is E naught cosine kx minus omega t, right? Everybody is comfortable with that. It's a plane wave that's incident on the slab of material. And then I wait time delta t, let the wave propagate through the material delta x. But for a second now, assume there was no material. Okay. What would be the wave at the point over here? Yes, please.
K delta x minus omega t.
K delta x minus omega delta t. Is that the wave?
Maybe not.
You're close, but you forgot the original term, kx minus omega t. So it will be k x plus delta x minus omega t plus delta, right? That would be the wave, is what I'm saying. Okay, that would be the phase. So, but the change in phase, if I call this part the phase phi, this is the phase phi plus delta phi, right? Right? Then delta phi is indeed what you just said. It's k delta x minus omega delta t. Everybody on board with this? Yes? Well, from this, we can ask what is the velocity of the wave? How do we ask that? Remember, the velocity of the wave is, or the phase velocity of the wave, is the velocity with which a constant phase front propagates. Okay? Meaning that in a time delta t, the change in the phase, how much does it propagate? Okay, so I divide both sides by delta t, right? So this is equal to k delta x over delta t minus omega. And so if this has to be a constant phase front, meaning the phase here and the phase here are the same or differing by 2 pi, but we are neglecting that for now, then we have to set this equal to 0, right? And therefore we get that k delta x over delta t equals omega over k, which means the velocity v is equal to omega over k, okay, which is correct. We know that in a free space with nothing, no material in there, the velocity, which is the speed of light here, will be equal to omega over k.
Is this also the dispersion relation?
Yeah, it is the dispersion relation in vacuum. Yeah, this is a vacuum. Assume for now that there's nothing, right? No medium. This is just vacuum on this side, vacuum on that side. I've just taken some little piece of material delta X. For now, even that material is not there, but the argument is valid for anything. Okay.
So how does this related to the one? So at the beginning, we are solving the PDE. The PDE
It's the same.
the same.
Yeah, it's the same form. Of course, we're specialized to a plane wave for this argument. Yeah, special case of plane wave for this argument. But that dispersion relation is more general, right? It's true for any sort of, well, actually, that's also for plane wave also, because to get it, you have to assume e to the ikx and put it in there to get this same equation for the dispersion. So plane waves, yeah. This is a more physical way to. Everybody okay with this argument so far? Any questions? Yeah.
I just wondered, I think delta x is related to delta t, is that correct?
Yeah, delta x over delta t, I'm calling the velocity. Yeah. Velocity of the wave, the phase velocity.
Yes, so you get from the original equation to the second equation. I don't think there need to be a delta. I think we only need to change the t term because we are waiting for the delta t, and we don't need to change the x.
I'm saying this change in the phase going from here to here can be written in this form. I'm of course setting it to 0 because it's the same phase front. The phase front has just gone from here to here. So the phase, this left hand side is effectively 0, basically. Yeah. It's the same phase front, it's just propagated forward. When you change the time by delta t, the phase front has moved forward by delta x.
Yes.
So that's what I've written.
So okay, I'll think about this later.
Okay. All right, now let's put in our material over here. So now instead of just being empty space or vacuum, I put in some material. Okay. And the effect of this material, right, as I just told you, is to just add a phase lag to the wave. Okay. Right. So instead of being this phase over here, now delta phi, instead of being k delta x minus omega delta t, I'm going to add an extra term, epsilon. Okay. Okay. And I'm going to say this, what do we know about this epsilon? Well, first of all, it's obviously got to be proportional to sort of the thickness of that material, right? Thicker the material, the more the phase is going to shift as I go through it. So I say of epsilon proportional to delta x. And of course, I need to make this something dimensionless because it's a phase. So I'm going to argue epsilon is k times delta x times some dimensionless constant, which is dependent on the material of this little slab of material. I'm going to represent that little constant by something called n minus 1, where n I'm calling as the index of refraction. Just go with me for a second and you'll see where this leads. Okay. So delta phi is now k delta x minus omega delta t plus k delta x times n minus 1. Again, we want to find the phase velocity. So again, I divide by delta t. I set this equal to 0, mainly because it's the same phase. The same phase front has propagated from left to right. So the phase has remained a constant. So the phase change in phase over change in time must be 0. Okay. So k times now the phase velocity delta x minus by omega by delta t minus omega plus k times v times n minus 1 must be equal to 0. Okay. So now I solve for v. Well, as you can see, this KV cancels with this -1 over here, right? And so it's just a very simple solution. V equals omega over K n. Right? Everybody okay with this? Okay. Omega over K is, of course, the velocity of light without the medium, without that slab, which I'm going to call C in vacuum, right? This is that V that I derived here without any medium. This I'm going to call as C, the velocity of light in a vacuum. Okay. So this is C divided by n. Okay, so the phase velocity in the medium is equal to the velocity of light divided by n, the refractive index. So that phase lead or phase lag basically gives me a new velocity for light. This is called the phase velocity. Any questions? Yes.
For the change in phi or for the change in t, could you just explain again why that's equal to 0?
It's the same reason why we set it to 0 here. So should I explain this first? Okay, good. Okay, so it's the basic reason is I have a phase front here. I let it go for some time delta t. I run the clock forward, and I've said the phase front goes forward a length delta x. So the phase front hasn't changed. It has just moved from position x to position x plus delta x. So the phase on that wavefront must be the same as it was before we ran the clock forward by delta t. So delta phi equals 0, basically. Yes.
So in for some materials, so we have a negative refractive index.
Great. Let's talk about that for a second. Okay. Great. But any other questions before we talk about it? Yes.
So delta phi over delta t is 0 because the phase is only changing in position.
So a phase front is, let's say I labeled the phase front as having a phase, let's call it, I don't know, 2 pi. No, 2 pi is a bad thing. Let's say 2 pi over 3. Okay. All right. So the phase on this wavefront, let it be 2 pi over 3. We wait a time delta t, that phase front has moved to the position x plus delta x, but the phase on it is still the same. It's still 2 pi over 3. All that's happened is that where the phase front equal to 2 pi over 3 has changed. That's how a wave is defined, right? It is, it's not the atoms or the molecules themselves that are moving, it's just the location of where the peaks and the troughs are that is changing. Okay, and this particular peak or trough, whatever you want to call it, has moved forward by that amount, but its phase has not changed.
So is delta phi over delta t always 0?
Yeah, I mean, in this case, because we're following one wavefront as it propagates through the medium. So its phase remains a constant throughout. So all I'm doing is, imagine I were an observer. This is famous Einstein's thought experiment. I'm surfing the light wave. Right? You guys know about the famous Einstein thought experiment, right? This is how he came up with the theory of relativity. At least that's the story. That he tried to imagine himself what it would be like to be on a light beam, to travel along with the light. Okay, and from that he came up with all those beautiful ideas in the theory of relativity. So think you're a surfer on that trough or peak of a wave. Okay, and now you're running time forward. You still want to stay on that peak. Well, you got to move forward a little. Okay, how much do you move by? You move by delta x over delta t, right? In that time, and so your velocity must then be delta x over delta t. But your phase has not changed. You're still at the same phase. Does that help?
Yeah, I think I get.
Okay, cool. Hey, great. Thank you for all the great questions. All right.
You said Einstein is that the constant speed of light for all the inertial frame?
Yeah. So
Yes,
I mean,
I think-
okay. So this is a story. I don't know. This is like a story I've heard or maybe read in one of his autobiographies, or maybe just like a kind of statement that people throw out that when he was trying to understand or explain all the contradictions of like Michelson and Morley and the fact that Lorentz transformations and all this stuff was already out there.
I think.
Well, can I finish? The claim is that he thought about himself being on a light beam. Like, what would the world look like if he was on a light beam? That was his,
But essentially, it's a fact that all the Maxwell equation, the form of the Maxwell equation is the same for all the inertial frames.
exactly.
So, and then in order to preserve that, so
Right.
it can have a constant speed of light.
Exactly. So his point was Maxwell equations are invariant. Well, if you want to go in a little bit more advanced language, Maxwell equations are invariant under Lorentz transformations, but not Newton's equations.
Yeah.
Okay, Lorentz transformations are out, already. Like people are out. But that wasn't how he thought about it, as far as I know. But anyway, that is the other way to say it. Okay, so we have now understood why a phase shift is so important. This is a very nice thing to know, that the phase shift from that scattered wave is the reason why there is a phase velocity that is different. So that's why the phase velocity, and so as we just saw, the phase velocity v is equal to c divided by n, right? C divided by n. So when n is greater than 1, v will be less than c. And on this side of the resonance, we have just argued that same phase lead is now a phase lag. Phase lag is now a phase lead, which means that now you're going to get n lesser than 1, which means the phase front must be propagating with a speed greater than c. Okay. You may be worried about this, but don't worry, because it's exactly the reason why we've been following this peak of the wave, right? Following the peak of the wave doesn't give us any new information. If it's a true sine wave that exists from this end of minus infinity to that end of minus infinity, then knowing that you're on the peak doesn't give you any new information. Okay. The peaks don't convey any extra information if they really do exist for all of infinity, from minus infinity to plus infinity. Or said another way, the fact that I know what the phase is at this point predicts forever the phase of the wave at all times and all space. It doesn't give me anything new. Like if at time t equal to 0, I told you this is a plane wave, it exists for all time or all space from here up to infinity with this equation a sine kx minus omega t. That's it. I've locked in all the information that I can ever tell you about this wave. The only way to convey new information is by changing something about the wave. Okay. So for example, I could say, oh, wait a minute, at this time, I'm going to add a second wave in, or at this time, t equal to 0, I'm going to shut off the laser or something like that. Now you can ask, how fast does that information travel? The fact that I shut off the laser beam or turned off the light bulb, flicked on the switch on the wall to turn on the lamp, or turned on this projector, whatever. How fast does that information travel? It turns out that's a different velocity. It's called the group velocity, which I'll come back to later. Okay? Does that help? Maybe. Okay. We'll have to come back to it. But the point is, phase velocity does not give us information velocity. Maybe that's a better way to say it. Or it does not tell us how fast changes in the wave will propagate outward in time and space. Okay? And that's what we really care about, new information. Okay? All right. And that's why it doesn't violate the special theory. Okay? So that's what I was just summarizing here. The fact that there's phase lead on this side, phase lag on that side, results in a different velocity, and the reason I've explained to you why it comes about mathematically. That's it. Okay. So to summarize, just give me a couple more minutes. Okay. Photons travel only at the speed of light, speed c, but light appears to slow down in most dense materials. So in most dense materials, we're well below that resonance frequency. Omega is far lesser than omega naught, because omega naught is usually in the violet, ultraviolet, etc. for most molecules and atoms and so on. So the transmitted wave is the sum of the incident and scattered wave. And we just said that there is all this phase lag. Okay, I'm not going to go into this stuff. I already told you the reason why.
So I have a question. So here you talk about photons and then it's slow down. But does this apply to any massless particles? So
there is some analogies I can do to phonons as well and things like that. But I don't have time for it. Can I just get through this?
Phonon is a quasi-particle. I said the massless elementary particle, so they all propagate as
if they follow the same type of physics, yeah, they'll have this behavior. Okay, so I have one last Canvas quiz. I guess I don't have time. I will open it up and you guys can answer it today. What happened? Uh-oh. Click the wrong button. Okay, yes. So the quiz I have for you, which you're free to talk to your friends about and try to answer, I think it will be fairly obvious. You may not even need to consult much. The reason the moon sky is black. Okay, so if you're sitting on the moon and looking upward, you don't see blue light. You don't see, sky, reddish orange sunsets, etc. You all probably. But I just put it up there. This connects back to, of course, our discussion of scattering and all that. So I just put it there, and it'll be up on the canvas, and so please answer it today. And I'll open up a discussion as well. Why do clouds look white? Okay, so we've talked about why the sky looks blue and why there's reddish and orangish light and so on. But we can also ask, why do clouds, which don't seem to look blue or red, they look mostly white? Why is that? Okay, take some time to think about this and put your answer on the discussion. Okay, all right, I'll stop there.
Yeah, so I asked you about for any mass particle